Welcome to this instructional video about water and weak acids. Water has a very interesting property. It is said to be amphiprotic, which means it can act as an acid or a base. So let's look at this image up here. This water molecule is acting as a base. It is abstracting a proton from water, another molecule of water, and so this one is accepting the hydrogen ion, and this one is said to be donating the hydrogen ion, and therefore water can do both jobs, an acid or a base. So we call it amphiprotic. Now notice the equilibrium here. So when two water molecules react in an acid-base reaction, you're going to get the hydronium ion and the hydroxide ion. And there is an equilibrium established. Now, what we can use is a very important equation called the ion product of water. It is known that the product of the concentration of the hydronium ion and the hydroxide ion is always 1.0 times 10 to the minus 14th. Now, just to keep the units straight, I call this molar squared. Now, concentration squared is not really a valid unit, but that's a good bookkeeping for units later on. So let's go with it. So this is the ion product of water. Again, if you know how much hydronium ion is in a particular solution, if you know how much hydronium ion you have, you can always calculate how much hydroxide ion that you have because of this relationship defined by the ion product of water. Now, what we know is that pH, something you've heard of before, I'm sure, is an important property of an aqueous solution. So this is a kind of a hot button issue with me. pH is the property of a solution, not of a molecule. Okay? It is the property of an aqueous solution that has acids and bases dissolved in it. Okay? We all know about the pH scale. It goes from 0 to 14. 7 is kind of the important dividing line here. 7 is said to be neutral, and if you get a pH higher than 7, you would have a basic solution. And if you go down below 7, you have an acidic solution. And some of these things on here, this is not anything to memorize. It probably it's pretty intuitive. Something like tomato juice has acid in it, so it's going to be acidic. Human gastric contents, very acidic. Something like human blood plasma is slightly basic, just above 7. Well, there's just some things we need to be able to do with pH, and one is to do a couple of calculations. So let's write down a couple of important equations. If you want to know the pH of the solution, it is minus the base 10 log of the concentration of the hydronium ion. Now let me give a little warning here. Sometimes we use hydronium ion and hydrogen ion interchangeably in these types of equations. But technically, the way it's typically written, pH is minus the base 10 log of the hydronium ion concentration. So if you know the hydronium ion concentration, you can calculate the pH of a solution. Also, if you know the hydroxide ion concentration of a solution, you can calculate the hydronium ion concentration by the ion product of water equation. And then once you have the hydronium ion concentration, you can calculate pH. We can kind of go the other way. If you have the hydronium ion concentration, the hydronium ion concentration is 10 to the minus pH. So if you know the pH of the solution, then you can calculate specifically what the hydronium ion concentration is. Now, Again, I don't think this is groundbreaking news to you. Sometimes we don't need to do specific calculations. We just can look at the hydronium ion concentration or the hydroxide ion concentration and make some decisions about the solution. So if the hydronium ion concentration is exactly equal to 10 to the minus 7th molar, the solution is said to be neutral. And according to our equation on the last page, pH will be 7. If the hydronium ion concentration is greater than 10 to the minus 7th molar, by definition, the solution is acidic. And of course, the pH will be less than 7. We know that. If the hydronium ion concentration is less than 10 to the minus 7th molar, the solution is said to be basic. And the pH will certainly be above 7. So let's review some definitions and some issues here. Again, hydrogen ion and the hydronium ion are often used interchangeably. Some other things we need to understand is the definition of an acid and a base. Well, an acid donates a hydrogen ion, or it dissociates in water to produce a hydrogen ion. Okay? A base accepts a hydrogen ion, or it dissociates in water to produce a hydroxide ion. Those are the kind of the working definitions of an acid or a base that you have likely seen before, and we will use these over and over again. If we go further and just talk about acids, you know, we have strong acids and bases. They dissociate 100% in water. So the poster child for that is HCl. You put it in water, it dissociates 100% to hydrogen ions and chloride ions. There's no HCl left. Weak acids and bases do not dissociate or ionize 100% in water. So kind of our abbreviation for a weak acid is HA, let's say. Again, this is just an abbreviation. It will dissociate in water. Notice I've got the equilibrium arrows here because we do not have 100% dissociation. We get H plus plus A minus. Again, there is not a complete dissociation. There's going to be an equilibrium. So you will always have some fraction of the molecules in the HA form, and then some fraction of the molecules will be dissociated into H plus and A minus. And we'll learn later in this class is that pH of the solution will dictate which one is favored, which two sides of this equilibrium will be favored. The last thing I want to do in this video, we're going to expand on this more in class, but is talk a little bit more about weak acids. Probably one of the best known weak acids is acetic acid, the main component of vinegar. Organic acids, carboxylic acids, are typically weak acids, and so you can put them in water. I'm not showing water in the equilibrium, but you could if you wanted to. I'm just going to show the acid form here, and it's going to dissociate into the base form plus H plus. Again, acid form and the base form. Every weak acid has a constant called Ka. And Ka is an equilibrium constant that you've learned about in general chemistry. And so in this case, Ka is the concentration of the base form, or you might call it the conjugate base form, times the hydrogen ion concentration, divided by the acid form concentration. Okay, and again, you probably have had this in general chemistry as well. The acid dissociation constant. So we know stronger acids dissociate more in water. Stronger acids dissociate more in water. Let me say it again. Stronger acids dissociate more in water. So what we know, if we come over here and say stronger acids, will have higher Ka values. So the more dissociated an acid is in solution, the more the conjugate base and the hydrogen ion you have, which mathematically makes the numerator higher than the denominator, and so we're going to have, or tends to increase those, the numerator versus the denominator, so Ka will be a larger number. So stronger acids have higher Ka values. So this is a handy way to identify acids that are stronger or weaker than others. Now the issue is we don't always use Ka, we use pKa, which is minus the base 10 log of Ka. And really the reason for this is Ka values are in scientific notation. And some people don't like to use scientific notation. So just take the minus log of the Ka and you get a number that's easier to work with than something in scientific notation. So typically we're going to stick with pKa over Ka. But you need to understand how both of these work. So in this case, stronger acids have lower, smaller pKa values. So you can determine if one acid is stronger than another by looking at their pKa values. And typically I'm going to ask you to explain why one acid is stronger than another, and then we can use pKa to tell which one is stronger than the other. But many times I'm going to want you to give me a chemical explanation of why one acid is stronger than another. pKa is just a way to rank them and know the order of acidity, but we're going to need a more in-depth chemical explanation as to why something or a molecule is more acidic than another molecule. Alright, this concludes this video on water and weak acids.